Hello everyone, my name is Jian Yang. Today I'm presenting to you our work MTAG, Modal-Temporal Attention Graph for Unaligned Human Multimodal Language Sequences. This is a joint work between CMU and SUTD. Here is an outline of our presentation. So let's start with what multimodal sequence is. Multimodal sequence is a data that is sequential and recorded in multiple channels. For example, video is a multimodal sequence. In the healthcare domain, the vital signals of a patient form a multimodal sequence. For autonomous vehicle, the camera and LiDAR attached to the car also form a multimodal sequence. So why do we care about multimodal sequence? Well, there are very abundant data in this format. Video platform like YouTube and video conference platform like Zoom, these are all platforms that generates tons of such data every day. And with abundant data, there comes diverse applications. For example, we can do sentiment analysis and emotion detection on video data, and using the vital signals of a patient, we could potentially do disease prediction. So what are some of the challenges in multimodal sequence? Well, there are 4 challenges, and then the first challenge is the irregular lens problem. So take, for example, the example on the right. Say we have 3 modalities in a video, and you may have 6 features in the video modality, and then 5 tokens in the text modality, and maybe 10 syllables or utterance in the audio modality. And with those irregular lens, there also comes the problem of misalignment. So misalignment refers to the problem of how you correspond feature in one modality to feature in another modality. Remember, these features are given to you in a sequence. So traditional approach has attacked this problem using hard word-level alignment, but such approach suffers the drawback of needing more supervision. Specifically, we would need the time interval for each of the token in text modality to be able to correspond the other 2 modality to the text. And also, such approach just requires more engineering effort. It's a non-trivial task to impute and align the other 2 modalities to text. So the third challenge is the fusion of more than 2 modalities. So traditional approach has attacked this problem using pairwise cross-modal attention. So we can model vision and text interaction, and then we can model audio and text interaction, but they can only do this in a pairwise manner. This means for a video sequence that has 3 modalities, you would have to do 6 such modules to be able to model all pairwise interactions, which in turn translates to lots of model parameters and a lot of computation. And the last challenge in multimodal sequence is the long-term temporal dependency problem. Say you have a sarcastic sentence in a video, and maybe that information is only, you can only decode such information if you know there's a high pitch in the audio at the beginning, and there's a certain token at the text in the end of the text modality. So these type of a long-term dependency is required in modeling multimodal sequence. So why is graph a suitable choice for modeling such data? Well, graph have the advantage of we can conveniently add nodes and build edges. So the first characteristic of adding nodes conveniently solves the problem of irregular length. Whenever you have a longer sequence or you have additional data in one modality, you can just add that data as a node into the graph. And then the second advantage of graph, which is building edge conveniently, that is a really powerful characteristic because we can basically indicate our intended inductive bias and the possible interaction between modalities. Just add an edge in the graph to guide the model to model such interaction. We'll dive into more detail about this. So for our method, the first step in our method is node construction. This refers to the step where we convert multimodal sequence data into nodes in the graph. Specifically, imagine we have 3 sequences, one in text, one in video, and one in audio. And then we would convert each vector in one modality into a node. Specifically, this is done by first passing the vector through a feed-forward network and then adding a positional embedding to the vector. And the final product vector will be added as a node into the graph. So with all those nodes constructed, we would then construct the edges between these nodes. So we come up with a way to construct modal-temporal edges between these multimodal nodes. For the time being, please refer to our paper for more details on how exactly we construct these modal-temporal edges. And after we constructed the nodes and the edges, we have a complete graph. And then the next step is to do fields and pruning, to learn interactions between these nodes. And so on a high level, we combine this fields and prune operation into one layer, and then we would have n layers of such combination in our architecture, where n is a hyperparameter. So the fields operation is added because we want to combine information from different modalities and temporalities. And then the prune operation is added because we have such a dense graph with lots of nodes and lots of edges. So edge pruning can reduce the number of edges, which in turn reduces the computation and memory consumption. Also, pruning would serve as a regularization for training. So here is a close-up look of the modal-temporal attention fusion operation. So the important thing to note here is that each edge uses a temporal and model-specific attention vector. You can refer to our paper for more details, but there are 9 types of modality edge type and the 3 types of temporal edge types. So in total, you can see that we have 27 edge types in our graph. We evaluated our method on 2 datasets. The first one is called AMOCAP. AMOCAP is a video emotion classification dataset. And the second dataset is CMU-MoZ, which is a video sentiment analysis dataset. So on AMOCAP, our model is able to achieve the highest F1 score on all emotions. And on CMU-MoZ, our model is also able to achieve the highest score on most of the metrics. And it's worth mentioning that our model is very parameter efficient. Compared to the best previous method, our model only uses 0.14 million model parameters, whereas the previous method used 2.2 million parameters. So almost 20 times reduced in number of parameters. We also had some qualitative analysis in our paper, but again, for the time being, we won't have time to talk about it in this presentation. But the takeaway is that our model generates interpretable results. It provides a good visualization of the interaction learned. We also conducted the ablation study on our model, and it had 3 findings. The first finding is that adding modality and temporal specific edges improves performance. The second finding is that our top K edge pruning technique indeed improves performance. We also compared to a random pruning baseline and find that random pruning would actually decrease performance. The third and last finding is that language is the most helpful modality. And also we find that as we increase the number of modalities as input to the MTAG model, the model performance increases. So that wraps up our presentation. Here is a summary of our contribution. We propose a new pipeline using graph to model unaligned multimodal sequence. We design a new graph convolution operation called MTAG fusion. We achieved state-of-the-art results on 2 datasets, and our model was using much fewer model parameters than previous SODA. So, yeah, please feel free to check out our code and paper. Both of them are available online. Thank you for listening.